So, starting chapter 5, we're going to focus a lot on this idea of stereochemistry. And stereochemistry is going to be describing a lot about how your molecule exists in 3D space. And there's going to be a new term that we're going to focus on, and we're going to be thinking about this idea of stereoisomers. We've talked about the word isomer before. Isomers, especially constitutional isomers, are going to be molecules that have the same molecular formula, same amount of carbons, oxygens, hydrogens, so on and so forth, but the way in which they're connected is differently. The idea of a stereoisomer is you actually have all of the exact same atoms, but the only thing that's going to be different is how they exist in 3D space. And we actually kind of were able to see a few examples of those last chapter, even though we didn't formally call them out or give them a name. So when we're thinking back to like our chair structures and we have a cyclohexane, I have two that are drawn here. Both of them are di-substituted. They both have two chlorines. And on the top one, both of those chlorines are, they have a wedge. And that wedge, for example, we're going to describe as up. And we'll see that those chlorines, we have a axial up chlorine here, and then we have an equatorial up chlorine there. Another name that we kind of came up with was when we were thinking about the idea of two different locations. In this case, our locations where our chlorines are. If they have the same directions, both of them being wedges, we're going to call those cis, which is going to mean the same. Where if they're different, or if you have a wedge and a dash, we'll call that trans. If we then look at, for example, one where we move just one of ours to a down position rather than up, here we'll see that we have an equatorial down and our original equatorial up. And we'll remember that the difference between the stability of these are going to be drastic. The very first one, that cis isomer, has a lot of 1,3 diaxial interactions because of the fact that it's going to have an axial up, where this trans, being two equatorial, are going to be a lot more stable. And the only thing that we changed is purely just the direction or the location of where that chlorine was. It's still on the exact same carbon. We can call it like carbon 1 or carbon 4. All it did is just went from an up to a down position. And that's going to, then that can have a huge impact on properties. And we're going to spend a lot of time thinking about molecules and how they're arranged in 3D space and some of the impacts that it will have. So the first is going to be kind of a term that we're going to define, and it's this term enantiomer. In our next video, we're going to spend a lot more time talking about the idea of an enantiomer and a diastereomer. But kind of just thinking of that word, enantiomer is going to come from the Greek word enantio, meaning opposite. And there's going to be a phrase that we're going to use a lot that you'll kind of have committed to memory. Enantiomers are non-superimposable mirror images. And that's a big, complicated word, non-superimposable mirror images. But it kind of makes sense when you start thinking about things in space. So take your hands, for example. If I look at, stop shaking. If I look at my two hands, they're mirror images of each other. If I imagine a mirror plane directly in here, my thumbs are on the same side, my pinkies are on the same side. They're a mirror image to each other, minus a few like little like nicks and bumps and irregularities, but generally they're a mirror image. However, they're non-superimposable. So if I take one of my hands and I rotate it around, it does not go on top. My thumbs are on the wrong side. So the idea of superimposable is if you take it and then try to lay it directly on top. So in this case, actually I should not have done that. There we are. So if they're both like palm facing, they're not superimposable. Now molecules can have that same property. So here I have a molecule. I just have a bunch of generic colors with it. So we have a black ball, a red, a blue, a yellow, and a white. And those are going to be 4 unique attachments. And that's going to be something that we're going to really establish as a core theme, that in order to have a stereocenter, most of the time you're going to need unique attachments on everything. So I'm going to go ahead and grab a second one. So I now have 2 of the exact same molecules, same red, blue, yellow. And I'm going to go ahead and line these up where they're mirror images. So you'll see that the blue is on the same side, the red is on the same side, yellows are away, and whites are on the top. If I take this, I see that these are mirror images, but if I rotate this around and then try to superimpose or put it on top of it, you'll notice that your red and blues are actually on the wrong side. Those are not superimposable. And that has almost in many ways, if you think of like a screw, there's like a directionality when you're trying to do the screw when you have like a righty tighty, lefty loosey. Same idea, where there is a rotation that's going to be associated with your molecules. And this is going to come up with this idea of the word chirality. So chirality, coming from the Greek word meaning hand, is going to be the geometric property that arises from your stereocenter. And most of the time, we're going to be thinking about carbons, although they can be other atoms, that are going to have tetrahedral geometry and 4 unique attachments. And you can have a bunch of different chiral centers. A chiral center is going to be a location on your molecule where there is some specific directionality associated with it based on an arrangement of, generally speaking, 4 unique groups. We have an example here of lactic acid, and the 4 unique groups are a hydrogen, an alcohol, a methyl, and then a carboxylic acid. Now, this has a huge impact on the properties of some materials, and I kind of have a handful of different examples here. So for artificial sweetener, you can see the difference between L and D. L and D, as well as plus and minus, and R and S are going to be descriptors to use whether or not it's going to be like right-handed or left-handed. And you'll see that one of the forms is tasteless, where the other one is sweet. Another example, so here is a essential oil, and in the one form, you have a taste that is like spearmint. The other one has a taste of caraway. And the only difference is just the single spatial arrangement of the 4 groups around that red dotted atom. You can even see, and one thing that we'll see probably the most common examples are going to be in a lot of medicines. If you are trying to design a new medicine and you want to get that like approved for like humans to be able to take it, the chirality or the very specific arrangement of things is super, super important. There's going to be a term that we're eventually going to learn called a racemic mixture. And if a molecule is racemic, it's going to have a random mixture of both of those 2 different forms, your R and your S, which are going to be terms we're going to learn in just a second. If you have a racemic drug, the chance of it getting approved is probably really, really low. To kind of give like 2 examples here, here is a antidepressant drug, and one of its forms is really effective as an antidepressant. The other one has no impacts. Some can actually not just simply have like no impacts to some impacts. Some can actually have some negative impacts. So here is an example of associated with safety, where one of the forms treats rheumatoid arthritis and the other is actually toxic. And simply just changing how things exist in 3D space can have huge impacts. Now, a lot of that is how it actually interacts, for example, like with like a protein. One of the forms will fit in a protein in a specific way. If the 2 groups are switched, it actually can't dock, for example, with a something associated with biology. Now, there is going to be a bunch of different terms, and I kind of had a bunch of them shown here. L's and D's, pluses and minuses, R's and S's. Those are all going to be different terms that are going to be used to describe our stereochemistry. For a kind of quick snapshot, the ones we are going to use the most are going to be R and S. R and S are going to describe the stereochemistry of a kind of, or at a single center, single carbon most of the time. So there's going to be a single sp3 carbon that we're going to be thinking about the stereochemistry. L and D are a little bit broader. L and D is going to be kind of thinking about the entire configuration. Of your molecule. And then the pluses and minuses are optical activity. We'll do equals just so it doesn't look like another minus. So these materials will actually bend light in a specific direction, and that's one of the ways in which you can actually measure chirality through circular dichroism, or CD. And if you shine light and you see the light either turning to one direction or the other, you can have an instrument, or you can actually do it sometimes even just with eye, to actually find the difference in the optical activity. Now, what we're going to do is we're going to spend some time learning about the rules for RNS. And there is going to be a series of rules, which are the CIP, or the Kahn-Ingalls prelog rules, which we're going to focus on in the very next video. And we're going to be thinking about, if you look at a very specific stereocenter, how do you rank those 4 unique attachments? If we look, for example, at this antidepressant here, the spot that has your wedges and dashes are going to have 4 unique attachments. For example, one of them is going to be an oxygen. The second one is going to be like this benzene ring that has a cyano at the end. This third one is going to be a benzene ring with a fluorine at the end. And then this fourth one is going to be a few carbons out to an amine. And each of these we're going to go through, and we're going to learn some specific rules and how we're going to rank them. And then that's going to give us some handedness to know that whether or not this is going to have a clockwise or a counterclockwise rotation. And those clockwise and counterclockwise rotations are going to be where we come up with these terms of R and S. So you've gotten a little bit of preview about your kind of importance and ways in which we think about chirality. And in our next video, we're going to spend a bunch of time kind of learning these Kahn-Ingalls prelog rules. So we're going to stop there, and I'll see you in the next one.